This is Knowledge Engineering with Semantic Web Technologies, and this is lecture number 5, Ontological Engineering. What we want to do today in this extra part of the lecture, which is not a part of the official OpenHPI lecture, is we want to have a look at ontology evaluation. We already have covered the theoretical foundations of ontology evaluation in the course of our lecture, but we had no practical example how to do that. And for this, I want to introduce today a methodology which is called OntoClean, which is a practical tool for ontology evaluation. OntoClean focuses on taxonomical structures, which somehow are or build the backbone of many ontologies. So you have class hierarchies. And the question here, of course, is this class hierarchy modeled correctly or not? So the experienced domain modeler can see the correct way how to structure a taxonomy, but usually he's not able to justify the decision. And here come methodologies into play, like for example OntoClean, which gives you a means how for deciding is this a correct taxonomical structure or not. So the problem here usually is that these subsumption hierarchies usually are misused to represent relationships that are not necessarily a real subsumption. Like here, for example, you have OpenHPI cores is somehow a subclass of OpenHPI, but whether this really holds or not is really a question. So is this really a subclass? Is this a specialization of OpenHPI, of an instance of the class OpenHPI? Yeah, that is really a problem. So we need some means to decide that, not only as a human, but also we must have, let's say, some formal rules which gives us a help in deciding exactly that question. So we are focusing on taxonomies and subsumption. For this first, we have to formally define what a subsumption is. So a subsumption usually also is referred to as a relationship. So you say a thing which so a class which is subsumed by another class, you say this class is of the type of its superclass, for example. So therefore, it's used to construct so-called concept hierarchies. So the formal correct interpretation would be A class subsumes class B, so B is a subclass of A, if all instances of B are necessarily also instances of A. So if the instances of the subclass necessarily are instances of the superclass. So this is the formal correct interpretation of what is subsumption. And this must hold in your taxonomy, in your ontology that you do. So what it means, usually then attributes, properties and characteristics of superclasses are inherited along the hierarchy to all the subclasses. But unfortunately, the subsumption relation often is misused or confused with other types of relationships. And we want to have a look at a few examples for that. So consider the following example here. We say Harald is a subclass of human and human is a subclass of species. And human also is a subclass of mammal. So we use here this is-a relationship. Yeah, of course, is-a comes from natural language. And here it should mean something like being a subclass. But you see here several difficulties. First of all, we see Harald is an individual. So it's probably a member of the class human. It's of type human. Human is a class, of course. But then the next question is human a species? Is human a mammal? And so is human a subclass of mammal and is human a subclass of species? What we can say, yeah, for sure, humans are some kind of species. So therefore, humans could be an instantiation of species, a special species. But mammal can be a superclass, and both mammal and human, they are subclasses of species. So you see here, to model something like this might be confusing. And of course, not necessarily all what you decide being a class really is a class in that sense. So what you can do, for example, you can say Harald is an instance of human, and you can say human is an instance of species. Likewise, mammal could be an instance of species, and you can say human is a subclass of mammal. But this, you say, sometimes you see this is confused. Subsumption often is confused with instantiation, and we have to take care of exactly that and not to confuse it. Another thing, consider here, we say engine is a subclass of car. This might not be correct because, yeah, here it is confused with a part-whole relationship, how we can find out that. So some essential properties of car are so-called functional properties, like, for example, a car is able to accommodate people. Look at the functional properties of the engine. Here you have an essential property like an engine is able to crank or an engine is able to generate rotational force. I mean, the main difficulty here is that for both of the classes, the essential properties, they are not the same. So it means the essential properties of cars do not apply to engines and vice versa. So therefore, this is some kind of a modeling error, and you have to replace your taxonomic relationship with another relationship. Car cannot subsume engine. What you have to do here, for example, you have to say engine is a part of your car, but not a subclass. Might be clear, but you will see in the course of the next 2 lectures that this might be again a problem. So this doesn't hold. Another case of confusion is so-called disjunction of classes. So the question here is engine a subclass of car parts? Maybe you would say, yeah, engine of course is part of a car, but of course not all engines really are built in cars, so therefore engine is not necessarily a subclass of car parts. So here the point is not all engines are really car parts, like for example the boat engine. And vice versa, car parts again can be considered a subclass of the class that contains all possible engines, all fenders, all windscreens, all doors, all seats, and all the stuff what a car is built upon. So this would be some kind of an interesting subclass relationship. So you could say a car part is a subclass of this abstract class that constitutes from a disjunction of several other classes. So here this somehow can also be confused. So this is not a subclass relationship. Next point, constitution. So here we have the example, ocean is a subclass of water. Yeah, ocean is some kind of water, you would say. Yeah, but the problem lies deeper. So an instance of water, let's look at instances of these classes. An instance of water would be some amount of water. What is an instance of ocean? Yeah, for example, the Pacific Ocean, the Atlantic Ocean, they are all instances of oceans. So, but now you have the problem that oceans usually are made up of amounts of water. So therefore, an ocean cannot be again a subclass of an amount of water. So you have here a part of relation and not a subclass relationship. So this here again is a constitutional relationship. Subsumption has been confused with constitution, and this of course is also not allowed. Yeah, now the problem is how can we find these critical design decisions? OntoClean has been developed a long time ago, 2001, by Nicola Guarino and Chris Welty, and they have come up with a methodology that helps you to validate or to check your taxonomic relationships. So usually it's built or it's used for ontology validation, as we said, so it's checked whether really your ontology fits to what you want to model in the world, and it helps to expose common misuses of subsumption and provides a formal basis to argument. So why are these subsumptions sometimes wrong and why they sometimes fit? So OntoClean helps to expose inappropriate and inconsistent modeling choices, and it helps to expose implicit assumptions about the way in which atomic properties or classes have to be or are interpreted by the modeler. And on the other hand, also, it helps to expose ontological commitments that have been made by the modeler and that might be not necessarily true or right or correct. And it focuses usually on the taxonomy and on the subsumption relation. And for this reason, of course, again, it first states formally what subsumption is. So A subsums B if and only if for all x it holds that if X is an instance of B, this implies that X is also an instance of A. So the subsumption relation, like we have already introduced it, is the basic core of OntoClean. Okay, one of the problems of OntoClean is it has been developed a long time ago, even before OWL, for example. Therefore, it uses a slightly different terminology, but this shouldn't confuse you. I will sum it up for you here. So instead of classes, OntoClean speaks of so-called general properties. So they correspond to unary predicates in first-order logic, like being an apple, being a table, or being a person. And of course, usually they can be associated with classes. And classes are a set of entities which expose exactly this property in one of the possible worlds that they can be in. So we can consider general properties like classes, of course. And the members of the classes then are considered instances also of these properties. The point is you should not mix up this property, these general properties, which are the same as classes, and of course the OWL properties, which are relations. So these are two different kind of things. So we are talking, if we are talking about properties in OntoClean, we are referring to what we up to now have defined as being classes. So the next thing what we look at are so-called meta properties. And these meta properties describe particular characteristics of the properties, so of the classes. So what we are looking in these classes is we're looking for essence. Is this property essential for an entity, or is it not essential? Is it necessary? So for example, a person, if a certain person is not a person anymore, the entity is gone. So therefore, this is an essential class or an essential property. Then we look at rigidity, which is of course connected to essence. So we will see that later on. We will look at something like identity, unity, and also dependency. These are meta properties, and we use these properties to describe particular characteristics of the properties of the classes. And then what we do, we annotate all the classes, all the properties with these meta properties. And then OntoClean provides a set of rules which form constraints, and these constraints have to be fulfilled, of course. So we are associating meta properties then with properties, so which means the ontology classes, and this helps to characterize aspects of these properties. And with the help of constraints on these meta properties, we enforce restrictions on the taxonomy. And these violations, for example, if you detect a violation of these constraints, this helps to highlight and to evaluate choices at critical points within the taxonomy. Okay, so let's have a look. First, we have to consider essence and rigidity in OntoClean. A property is essential to an entity if it must hold for it, which means, on the other hand, so it's not just things that accidentally happen to be true all the time, it's essential. And then we are considering so-called rigid properties, and this is a property that is essential to all of its instances. So, for example, it's an entity, or it's every entity that can exhibit the property must exhibit the property. Every entity that is a person must be a person. So that's quite clear. And there are no entities that can be a person but that aren't a person. So then a property is rigid if it holds also for all the time. If a person ceases to exist, then the entity also ceases to exist. So therefore, person is a rigid property. Then we have anti-rigid properties, which are quite the opposite. So an anti-rigid property is one that is never an essential property. So for example, every student or every instance of student isn't necessarily a student. So students may cease to be students at some point without ceasing to exist or without changing their identity. So therefore, being a student is an anti-rigid property, an anti-rigid class. And if you consider classes for which, so if you consider properties that are essential for some instances but not essential for other instances of that property, then you call this semi-rigid. And of course, both of these classes you subsume as being non-rigid, so in comparison or difference to the rigid properties. Okay, let's go on with an example. Human, like person, of course, is a rigid property. Since every instance of human is necessarily also a human, and an entity can't stop being a human and still being recognizably the same entity. That's the point. So there are no entities that can be human but aren't humans. So at least not in our real world. So in difference to that, students is a non-rigid property, like we already said. So any student can cease to be a student while the entity is still the same. So it's still the same person. So that's an example for rigid and not rigid, so in this sense, anti-rigid properties. For the ontology evaluation now, what we do is we simply annotate all the classes. We label them accordingly with +r for rigid, with tilde-r for anti-rigid, and with -r for semi-rigid. So this means not rigid. The point then is meta-properties pose constraints on subsumption relations, which, for example, means a rigid class may never be subsumed by an anti-rigid class. So this is one of the rules that might be or has to be considered in the end, only to give you a first expression about that. So this is about rigidity. Now let's have a look at identity. Identity usually define identity criteria which allow us to recognize individual entities in the world. So this means that identity refers to the problem of being able to recognize individual entities in the world as being the same or being different. So identity criteria, rather important. Okay, let's look at the following example. Does this subclass relation hold? Is time interval really a subclass of time duration? Yeah, to understand that deeper, we should always have a look at instances of both classes. So let's have a look at instances of time duration. So this is 1 hour, 2 hour, 1 minute, 7 minutes. So these are time durations. And time intervals happen at a certain point in time. For example, 11 o'clock until 12 o'clock on Tuesday, November the 10th, or 18 o'clock until 19 o'clock on Saturday, December 2, and so on and so on. So you see there is clearly a difference. So interval seems to be more specific than time duration. Is it therefore really a subclass? Yeah, we have to look at identity criteria for the instances which are collected in these classes. And for example, for the time duration, you will find out that two durations of the same length are the same duration. So the length here is an identity criterion. What about time interval? Is this also then the most important identity criterion to have the same length? No. Two intervals at the same time and of the same length, they are the same interval. So you have to consider the point in time and the length. So this means many time intervals might have the same duration. So there is an ontological difference between the identity constraint or the identity criterion that we have here. Therefore, we are not allowed to model it as a subclass relation. It violates exactly this constraint, so it's not a subclass. So to do it in a correct way, so usually all time intervals are time duration. Yeah, since due to the ambiguity of natural language, this originally means all time intervals have a time duration. So yeah, duration is a component of an interval, but it's not the interval itself. So therefore, the correct modeling would be model time duration as a component of time interval. For our ontology evaluation, this means that all classes, again in the ontology, should label accordingly, +i for carrying a common identity criterion, -i for not carrying a common identity criterion, and +o for carrying an own entity criterion, which is not simply inherited by a class of which our class considered is subsumed. So the point is usually a property will inherit identity criteria from its parents, so then it will be labeled with +i, but it might also supply own and new additional identity criteria, and then it will be labeled with +o. This is identity. Next point after rigidity and identity is unity, so we are halfway through. Unity usually refers to the problem of describing the way the parts of an object are bound together. So the unity criteria identify whether or not a property is intended to describe whole objects. So a unity criteria should describe an object as a whole. For some classes, all of their instances are wholes. So for example, car. For others, none of their instances are wholes, like for example, water. So non-amount of water is the whole water. Yeah, that's the problem here. So consider the following example. We know this already. Can we somehow say ocean is a subclass of water? We have already discussed that. But here, again, if we look at the instances, so we look at the instance of amount of water, yeah, it's not a whole since it's not recognizable as an isolated entity. So again, here, water, it's difficult to identify an amount of water somehow. And the opposite holds then here for the ocean. So instances like the Atlantic Ocean are recognizable as a single entity. So here we have a criterion. So the point here again is if we claim that the instances of water are not whole instances and the instances of ocean are whole instances, then this results in a contradiction if we try to model it the way that we say ocean is a subclass of water. And of course we want to avoid that. So to detect modeling deficiencies like that, we should annotate again our classes here if a property carries a common unity criteria. I annotate it with +u. This is if all of its instances exhibit a common unity criterion, like for example ocean. And on the other way around, if a property carries no common unity, if its instances are all wholes, but with different unity criteria, like for example, a legal entity who has, for example, companies and people, and they have, of course, different unity criteria. A company as a whole is something different like people as a whole, so it's different criteria here. And then also you have to consider anti-unity. So a property carries anti-unity if all of its instances are not necessarily a whole, like we had it with water. So these are the three labels that we apply for unity. Either they have a common unity, they have no common unity, or they have a so-called anti-unity. So what we do for ontology evaluation, we label accordingly with +u, -u, or tilde-u. And the point here again is thinking about concepts identities while building an ontology helps to avoid and to discover mistakes that have been made during the modeling. So a whole class, for example, should never be subsumed by a not whole class. So this is one of the rules that have to be considered concerning unity. So now we have rigidity, we have identity, we have unity. Last thing that is missing is dependency. So when is something dependent of another thing? So here you can say formally a property X is externally dependent on another property Y if for all its instances necessarily some Y must exist which is never part or is never a constituent of it. So then it's externally dependent of another property. So let's look at an example. So for example, if you consider parent, parent is externally dependent always on child. So for a parent cannot be a parent without a child being there. So therefore parent is externally dependent on child. You annotate a property like that with +d. On the other hand, a person is not externally dependent on a heart, since any person has a heart, so it's a constituent, it's a part of a person. So therefore then, if it's not externally dependent, you annotate it with -d. So here in this small table, you see a small summary of all the meta properties that we have and of all the labels that we use to annotate the properties, which are nothing else but the classes in our taxonomy or in our ontology. So keep these in mind for annotation. We will use that. And then, of course, there are the constraints, the rules that have to be considered. And here are the 5 essential rules of OntoClean. So given two properties, P and Q, where Q subsumes P, which means P is a subclass of Q, the following constraints must hold. If the superclass Q is anti-rigid, then P must also be anti-rigid. If the superclass carries an identity criterion, then also the subclass must carry the same criterion. If the superclass carries a unity criterion, then also the subclass must carry the same criterion. As well as if the superclass has anti-unity, then the subclass must have anti-unity. So that's another rule. And of course, if the superclass is externally dependent, then also the subclass must be externally dependent. So what you do, you analyze your entire taxonomy, so the hierarchies that you have in your taxonomy, and violations of these constraints that you can detect with applying these rules, they help you to identify the problematic choices that have been made when the ontology was defined and where you probably have to reconsider. They help you also to extract a so-called conceptual backbone, which is made up of rigid properties from your ontology. Simply because rigid properties, they are invariant. They don't change over time, so you will get a backbone in your ontology, in your taxonomy, and that's some nice thing. So we come to an end. There are 2 additional rules to be considered in OntoClean, but they are minor rules, so additional rules for identity. It's the sortal individuation and the so-called sortal expandability. What do they say? So I will only briefly mention this. Every element of the domain must instantiate some property carrying an identity criterion. So this subsumes somehow the rule no entity without identity. So every entity must be identified somehow. And the sortal expandability means if something is an instance of different properties, so for example at different times, then it must be also an instance of a more general property carrying a criterion for its own identity. So every entity must instantiate a unique, most general property carrying a criterion for its identity. So you need these identities and somehow they must be there, and you must consider them, of course, during the modeling of your ontology. So these were, in general, in summary, the methodology OntoClean, which gives you means for ontology validation. We have now the entire theoretical concept how OntoClean works. In the next part of the lecture, I will give you a concrete example where we apply OntoClean exactly in the way like we have learned it.